Okay, we're ready for our first talk of the day. Sukumar Adhikari from on making a very long trip to talk to us.
Ahead?
Yes. Yeah, the pointer is kind of iffy. But...
Yeah. So first of all, I would like to thank Mail for kind invitation, and many years he is organizing and publishing the proceedings. Good job. Thank you, Kevin. So this is something and Ramsey theory related thing. Paul number theory is Van der Waals theorem. And so Professor Jean already made my job easy, but I have to go through the quick introduction that is for completeness, and also there may be young people attending who may not be familiar with this idea. And then applications, I have early applications, and there are two more sections for application. The last section contains some recent results. This is obtained jointly with Casio and L'Oreal. So that is still being finalized. So one result from this I will go to. So this is a notations. So coloring is nothing but a map to the colors from the set, and this is the color is that image of an element, and a subset is called monochromatic if it is constant on that subset, that color function is constant. And one observes that this is nothing but Disjordan partition, the coloring. So now, rightly finding its place among the pearls that Kinchin, he wrote this to a young warrior who was in hospital. And that was the origin of this book. And these three pearls, there were three very nicely chosen themes. One of them was Van der Waals theorem. And this, of course, as people know, led to many important development in combinatorics and additive combinatorics. So this is the statement, this is already mentioned yesterday, that for positive integers k and r, this wkr is that this is the finite version, that if you have these colors up to wkr, this is the Van der Waals number, then there is in r colors, then there is a monochromatic arithmetic progression of k terms. So the English translation of Kinchin's book came in 1952, and the original was there in 1947. And it is known that Graham and Spencer. See, there is a famous book, Graham, Rothschild, and Spencer, where people pick up their knowledge about the Ramsey theory nowadays. So they came to know about this result of Van der Waals from that book. And now there is a higher dimensional version I am mentioning, that this by Grunwald, and who changed his name to Galai. So in some book it will be Grunwald's theorem, some book it will be Galai's theorem. This is the higher dimensional version of Van der Waals theorem. This was submitted by Rado in 1939, and because of the war it got published only in 1945. So this is easier to show the diagram. So there is, if you take a finite set, here I have taken a finite set of 5 points, then there is a size within that, depending on the number of colors one uses and the particular set, you get a translated homotheity. So if we go back, this translated homotheity is like this. This is the homotheity, and then translated by vector B, and that will be within that. So in this thing, there is a monochromatic translated homotheity, and one you go to dimension 1 and put S, the consecutive numbers 1 to k, the translated homotheity of this is nothing but an arithmetic progression of length k. So that is. So the following statement follows from Van der Waals by induction. So this is equivalent to Van der Waals, but it is a bit powerful. it came immediately. I will mention what was the application of that. And so it is not only the arithmetic progression, but a chosen. You can choose a multiple of the common difference. They all are of the same color. So that is the so now I go to link this with some early Ramsey theorem, Ramsey's theorem also. So Ramsey's theorem is nothing but some sort of pigeonhole principle. So this is the pigeonhole principle, and so the particular case is some school exercise. So if there are 6 people in a party, they shake hands. So here I have written in the graph theoretic version the graph with 6 vertices, and you color the edges by 2 colors. Then there is a monochromatic triangle with all 3 sides. So from one point, if we have 5, so 3 of them has to be of the same color. To avoid this triangle monochromatic, you put blue, this blue, and this. So ultimately, you get a blue triangle. So this is very easy. And then now the generalization is Ramsey's theorem. This is the notation already introduced that is well known in number theory circle, that the consecutive integers 1 to n notation is this. And this is the collection of k-element subsets of the set A. So given positive integers k are L, and to avoid this thing, that L is taking greater than equal to k. So there exists a positive integer depending on k or L, such that for any R coloring of this is can work for any set with n elements, but we take this example. So all the k element subsets of these are colored are colored. Then there is an L element trait, the small L, so L number of elements are L, such that all its k element subsets are of the same color. So then Sur proved the following. This is 1916. So the Sur and Van der Waal in 1927, they are before Ramsey's result. So as yesterday it was mentioned that theories. So not only after Ramsey's theorem, it is 5 years after that once Edos-Jacquard's theorem came, and Edos went around lifting the subject, and then the subject of Ramsey theory came up. And with hindsight, one could see that some theorems before 1930 Ramsey's theorem, they fall in this, so that if you have a big structure, substructure of a big structure, either you partition into finitely many parts, then one of them is big. Otherwise, like Geminides theorem, if some sort of big means upper natural density positive or some way, then you have that part retains some regularity property. So that is the philosophy of Ramsey theory. And so this source theorem, given a positive integer R, there exists some depending on R, such that once you color this, there are monochromatic X, Y, Z of the same color satisfying this, and we describe this equation by saying that this equation has a monochromatic solution for a finite coloring of Z plus. And S equal to 1, if we put in this theorem, so that generalization of Van der Waals theorem with a chosen multiple of the common difference, I wrote as the theorem star because I may have to refer it 2 times. So in that, if you take S equal to 1, then the common difference is of the same color. So that the A and D, A plus D and D are of the same color, that implies Sur's theorem. So the Van der Waals implies Sur's theorem. And now Ramsey also implies Sur, because we take NR equal to N2 or 3. So there is a 3-color set, all of us 2-color subsets are of the same color, R colors are being. So this is very quickly you go through. We color this by, and now you color 2 element sets, Ij is nothing but the color of the difference of I and J, because the color is defined on the integers only. So by definition, there is the N2 or 3, so there is 3 element set, all of those 2 colors two element subsets are the same color, then this we get A less than B less than C, such that this is true, and then this we get, and this identity, then we get the source theorem. So Ramsey also implies so. Now we go to the application. First part, the early application. This is that's why this Alfred Bauer, he did that generalization with chosen multiple of the common difference. So that given any positive integer k, sufficiently large prime, so we have k consecutive quadratic residues and k quadratic non-residues. Residue is very easy because you go by that, take as many long as possible arithmetic progression with the common difference also same color. So if the common difference B is of the same color, then B inverse is also of that same color, residue or non-residue, and multiply that. If they are non-residue, then B inverse is a non-residue. So the product is always residue. So you get this part is easy. For non-residue one is a little more work. But nowadays much more is known because you give any pattern of residue, non-residue Rn, so any finite word that will for big prime it will work. Any pattern of but that cannot be done by van der Waals. For that character sums are required, but that is known. So this is just for remark. So let us go. So from Source theorem and a special case of so the Source theorem has a generalization in many directions. So one is that yesterday it was mentioned Folkman, Hinman. That's about. We will not go into that. We go to another direction. So we take this equation. Source says that this is regular. Regular means for any finite coloring there is a monochromatic solution, and then this is the three-term arithmetic progression. So now the common thing comes. This Rado was a student of Source. He did a very great thing that, but that is for system of equations. There is a column condition. I will not go into that. So that's why I mentioned abridged version. So for a single equation, the CI's are non-zero integer. Then when it is regular, then the necessary sufficient condition is that sum of the CI's sum up to 0. So that is here you take one of these, one from x and y, and one minus one from one sibling z, and here 1 plus 1 minus 2. So there are particular cases. So here this the proof there is the use of van der Waals theorem. Of course, the general result that system of equations when you prove, that is proved in a different method by, and from that van der Waals follows. So there is a lot of interrelation. So let me mention this way. So this is the regular. I already mentioned the word. So if this equation has a monochromatic solution with respect to any finite coloring, then it is called regular. So that the condition average version is sufficient, that follows from that theorem star. Okay, I will not go into that. And for necessity, one uses this coloring. In fact, this coloring can be done on non-zero rationals. Take the power this P out, and then A by B is now an element of the non-zero element in the finite field at P. So this is a P minus 1 coloring. So this is that. So this coloring has the property that by multiplying, if this x and y are of the same color, then multiple of that also are of the same color. Color may change, but they remain the same color. So with this also I am not going to the proof. So if none of the sum of the coefficient 0, then there is a prime which doesn't divide any of that, any of the sum, and that SP mod color what. So I will come to some question after that. So Rado made this one conjecture of Rado that if we follow this SP coloring, that this coloring and that prime which doesn't divide the sum of the coefficient, then that can go up and up. Even the number of variables remain the same, but to change the coefficients, you will require a higher more number of colors. But the Rado said that it is not needed. Actually, one can make, there is a conjecture. This is one of the most difficult conjectures in this area, that Rado's boundedness conjecture, that you don't need. So there is Rn parts, there is R is a function that depends only on the number of variables. And Fox-Kleiderman, so we state for a single homogeneous equation, because Rado already proved that if the conjecture is true for a single equation, it is true for a system of, and then Fox-Kleiderman showed that if it is done for homogeneous, then it is for any, even for non-homogeneous equation. And this is Rado's boundedness conjecture, as I mentioned. And this first non-trivial case, this Fox-Kleiderman proved, it is many years now, and beyond that, so they proved this, though it is not known whether this is optimal or not, but they proved that for three variable equation, whatever coefficient it is there, if it is not regular, then there is a color, you can use a coloring with less than equal to 24 colors, which can obstruct a monochromatic solution. So, but beyond that, that method, not going through even for four variable, that is difficult. There was another conjecture in this thesis of Rado, that there is a threshold, that where if it is not regular, then where the regularity breaks. So that is the degree of regularity. And there is a conjecture that for any positive integer n, there is some equation, linear equation, which has degree of regularity n. And that has been solved in last 2010, and there are a couple of papers that has been solved by giving different system of equations. And then, of course, the question remains that motivation is Rado's boundedness conjecture. So given a class of equations, you try to find their degree of regularity and see where it goes, whether. So there is work going on. We worked on both non-homogeneous and homogeneous equations, but we will not go into that. So there is another open question, that whether this equation is regular. Because if there are a lot of overlapping solutions, then that forces that monochromatic solution. So this is guessed that there may be, for two coloring, it is solved by SAT solution. That is that if you go up to this many, 1, 2, 3, up to 7, 8, 2, 5, then there is always a monochromatic solution of this. But if there is a coloring of 7, 8, 2, 4, then it fails, that there is no monochromatic solution. So one even knows that up to where you have to go for two coloring. But for three coloring, I think this sort of computing becomes very difficult. The computer may.
For three coloring is unknown or it's four?
No, unknown. Unknown. And people think, no, I also believe that this is true, conjecture, but the proof is difficult. Then there is, now we go to our second part, that Van der Waalen 2, that application 2, then there is a conjecture of Gurevich, which says that we color the whole plane by any point xy in the xy plane, but finitely many colors being used, but that can be very complicated once uses 20 colors given. Then it says that as long as the number of colors is finite, giving any delta, there is a triangle of area delta, but the three vertices are of the same color. And that was proved by Graham, in fact slightly stronger. Not only that, the stronger is that you can choose if you given any two intersecting lines, your triangle, two sides will be parallel to them. So with that, Graham proved. It was a bit lengthy and roundabout. So then I could manage some simpler two-page proof, but that is mainly Graham's idea only. Same thing, but I did some induction procedure, it made it simpler. Then there is another proof came. This I'll give the sketch of in 2010, Dumitrescu and Jian. This is simpler, but this doesn't have the additional thing that two sides are chosen direction. So the original Hurwitz conjecture is solved. Let me see so, but all these proofs are used by Van der Waals theorem being used. So what is this case? Suppose the alpha is given positive number and R coloring is given for the points. There is a typo. This is R2, okay, the plane. Okay, and so we can think lines being colored by subsets of the color which appear on the line. So there will be non-empty subset. Even the line is monochromatic, there will be one. So this is a subset of the number of color used, and so it is because empty is not there, so this is a 2 to the power r minus 1 coloring. Now define this Van der Waals number when this many colors are being used and the length of arithmetic progression is factorial r plus 1. So then n horizontal lines parameterized by the abscissa, then consider them. Okay, then by Van der Waals theorem, there is a parallel lines at a distance of k, so k2, k3. So this is the common difference, and all the lines are of that means same colors appear, same set of colors appear in all these lines. So now we fix this and take this r plus 1 multiples of x. Then because originally r colors are being used, there will be two multiples of the same color. So they are situated at a distance this. But then you go to the line factorial r by t. There also this color will appear. These two colors, A and B, are the same color. But all these parallel lines, they have the same set of color. So there will be a point on this line having the same color as A and B. And then what is the area of that? That is half into this Tx base, and this is the height. So that is the sum. So that is very clever. So now this question that I mentioned, that one question I would do, of course, that was bounded interest conjecture and all which I mentioned, they are like telling like Riemann hypothesis, they're very well known thing. But this conjecture may not be so well known, but this is pointed out by Graham already. This is not my conjecture, but I feel after trying for thing that it is true that for parallelogram. But then I tried for this parallelogram, but parallelogram we could not succeed. But then this with chain we could prove that for any positive integer r, there are two positive integers mr and nr, such that for any r coloring of the set of all integer points in the plane, there is a monochromatic trapezoid. Trapezoid you could prove with two sides parallel to the x-axis and all its vertices integer points, the diagonal this. So that doesn't depend on the particular r coloring. So, and this will not go, this is method is bit more involved. Okay, so we will not go into that. So then there is 3. Then we come to this some canonical coloring, some recent result as I mentioned. So this sky is a coloring, this is called rainbow. If this, so either if the number of colors is less than the number of points, then every color appears. Otherwise, all the colors are distinct if the number of colors is more. So we manage two type of definitions in this definition. So either all the colors appear, but if the number of points more, or if the number of colors more, then all colors are distinct. So this is the rainbow. Now the study of rainbow, I mean, structures are introduced by many people, and this is a result we will be using, Axanovich and Flass and 2004, that for every n greater than equal to 6, every 3 coloring, such that each color class, because here you have some constant is needed, because the line cannot be all colors should appear, not only they should appear quite big. So every color appears sort of 1/6. Then this contains a rainbow 3-term arithmetic progression. So this is the result of in 2004 result. Now what we do, this is the result. I will give the idea and show the sketch, then that is. So we are telling that 3 coloring is rainbow feasible if there is an integer n such that every interval of length n has in every horizontal line each color appears at least this many times. So this is not a very strict thing, but this is necessary. So in other words, we place the condition that the coloring ensures existence of 3-term arithmetic progression by that bond of Flass that earlier result. Now this, if chi is a rainbow feasible coloring of the planar integer lattice, there is an integer a independent of the coloring and a point such that there is either a monochromatic parallelogram or a rainbow trapezium. So this is very early. There was a result of Erdos and Rado. These canonical, they are called it either this or that. And then there is a Erdos and Graham on arithmetic progressions also. This van der Waals canonical version. So then we are doing this sort of result, the canonical version. So we get this result. So here a complicated coloring we go.
We're out of time.
Pardon?
We're almost out of time.
2 minutes. 2 minutes. Yeah.
2 minutes late.
Yeah. So we take a block of capital N integers that capital N comes from that result of we have quoted that condition we have taken. So by this thing, this contains a rainbow 3-term arithmetic progression, but then coloring now each Lij, that block can be colored identified by this. So what are these? This is the initial point that comes from X, and sigma is a permutation of 1 to 3. All 3 colors different. So the color 1, color 2, color 3. This is the permutation, and D is the common difference of the. So then this is about this, and then what happened? We are coloring now the lines the way that Dimitrescu's result was there. Now the coloring is so many, so we are taking that what colors appear in those blocks. But in a block, there may be more 3 tuples, but we choose 1 tuple and fix it. So we have to quickly go. So I'll go to the diagram and mention. So that will be, and the parameters are such that they cancel out. So the idea is like that. How is the diagram? The diagram I have to change, it is not properly written. So there is these 3 points, and these 3 points, and that alpha 1, beta 1, gamma 1 are the same color, alpha 2, beta 2, gamma 2 is same color, alpha 3, beta 3, gamma 3 are the same color. Take a point at a distance, whatever, from beta 2 to gamma 2, and that point Z, if that has the same coloring as alpha 2, beta 2, then you get a monochromatic thing of this area. Otherwise, what happened? Here, if it is different coloring, forget that coloring, then here we take alpha 1 and we take beta 3 and gamma 2. So here one less and here one more. So the area will be same, Z will be one vertex, and they are all, these 3 colors are different. But these 3 coloring, so no more coloring is expected. This Z can be of one of those 3 colors. So thank you.
Thank you.
Our next talk will start as soon as we can get set up.
For anyone interested, the book, Three Pearls of Number Theory by Finchon, it's a Dover paperback. It was unavailable for decades, but it's a Dover paperback for a couple of bucks. You might ask, so Van der Waals theorem is the first pearl. And what are the other 2 pearls?
There is Mann's theorem.
Mann's theorem, and the third?